Yeah, welcome everyone to our DP0 Delegate Assembly. So today we're going to be talking about mainly Trans-Neptunian objects in this DP0.3 solar system simulation. And I'm going to be the one presenting that. My name is Andres Plazas Malagon. Let me tell you a little bit about myself. I have a background actually in observational cosmology, with lensing and systematics. But about a year ago, I started working in the Rubin's community science team. And one of the cool things of working in this team is that you get to know a little bit more about the other exciting science that the LSST is going to do. So for this simulation, I got the honor and privilege to work on a notebook based on Trans-Neptunian objects, looking using the DP0.3 simulation. However, we do have an expert, a solar system expert in our team that is present. This is Sarah Greenstreet, and I'm very happy that she is around because then even for the hard questions that you have for me, I'm pretty sure that she's going to save me. So thank you, Sarah. And yeah, let me start with a few announcements as usual. So first of all, so we're gonna have the talk, and then after this, we're gonna have the possibility to have breakout rooms. So everybody is gonna have the chance to work usually in whatever they want, but of course you can work on the topic of today of the notebook of the Trans-Neptunian objects, and then we'll be around to answer any general questions that you have. Regarding the notebook, and then of course any questions that you may have about DP0.3 or even DP0.2, the extragalactic simulation that we have for Rubin. So yes, so that's gonna be whatever you can do in the breakout rooms. Okay, so that's gonna be in the second half of the presentation once I'm done with the going through the notebook. Okay, so the next week, so usually we have Stack Club in Interleaved with these assemblies, but actually next week we're going to have a special assembly. We're going to have another assembly continuing with the solar system theme. So we're going to have an LSST solar system science collaboration mini sprint preparation led by Meg Schwamp. And then, as you know, the solar system science collaboration is one of the 8 LSST science collaborations. Then 2 weeks from now, then we have another delegate assembly that is going to be presented by Christina Williams and Yumi Choi, who are members of the community science team, regarding a couple of notebooks that they, tutorial notebooks on DP0.3 that they wrote. And these notebooks are going to focus on what phase curves, that we're going to talk a little bit about that in this tutorial. So if you have access to the notebooks, probably you have already looked at that, and I'm pretty sure you have an account already, but please keep an eye on this and come to this assembly. And then at the same time, if you're working on your own project using DP0.2 or 0.3, we want to hear from you. So it would be great for you to tell us what the cool things that you're doing with these simulations are. So please don't hesitate to reach out to us, and then presenting one of these opportunities. This is going to be recorded and then posted on YouTube, and it's great visibility, and it's a great way of building the Rubin LSST community. So we really encourage our delegates or users to present in these assemblies. I also wanted to advertise a special delegate assembly that we have already booked in a few weeks from now, maybe, yeah, almost a little bit less than a month. And this is going to be an assembly dedicated to accessibility in Jupyter notebooks. We're going to have a researcher from the Space Telescope Science Institute, Jen Kotler, and then she's going to tell us about the importance of accessibility, and she's going to tell us about the authoring guidelines that we can follow in order to improve accessibility in Jupyter notebooks. This is an important topic within the community science team, and then we do have our own internal guidelines, and we've been trying to synchronize them with this type of authoring guidelines. But during this special delegate assembly or hackathon, we're going to have this presentation, and after that, Each one of you delegates are going to have the chance to bring your own notebook and work on implementing these guidelines and ask questions. So hopefully you can take advantage of this initiative. Let us know if you have any questions about this. I think that's it. Melissa, do we have anything else that maybe I may have forgotten, or we can go ahead with the presentation today?
Yeah, I think no new announcements today, so you're free to go ahead.
Sounds good. Thank you. And feel free to interrupt me. You know that this is very informal, and if you have any questions, raise your hand on Zoom or write in the chat. I'm not sure if I'm going to be able to look at the chat, but I'm pretty sure my colleagues will keep an eye on that. Okay, so right now, let me make this a little bit bigger. And okay, we have the usual view right now, the notebook aspect of the Rubin Science platform. Okay, yeah, we have a bunch of tutorials for DP0.2, about 12 of them, and then we're focusing on DP0.3, the solar system simulation, and so far we have 4 tutorials. This is the 3rd of the series, and if you have been following the assemblies or the recordings on YouTube, there have been a couple of other tutorials and a special presentation by some of the people who made the simulation, so I encourage you to take a look at that. The first tutorial was an introduction, and the second one was related to main belt asteroids. In this tutorial, we're going to talk about Trans-Neptunian objects, the Trans-Neptunian object population in the DP0.3. These objects are, by definition, are objects that are beyond the orbit of Neptune, about 3.1 astronomical units on average. And they're of scientific importance because they are like relics of the formation of the solar system, among other reasons. So this is one of the things that the people are looking forward to look at and characterize with the LSST data. So yeah, so as usual, we have the description of what we have in the notebooks and the type of catalogs that we're going to use in this tutorial. So in particular, we're going to use the MPC Minor Planet Center Orbital Catalog, the 10-year catalog, the 10-year observation of LSST. As a reminder, we have another 1-year catalog that you are welcome to explore. But here we're going to use mainly that MPC Orb catalog. Then the other catalogs that we're going to use are the SS object and the differential analysis source catalog. I wanted to mention that, of course, I didn't do this notebook by myself, so I wanted to acknowledge my colleagues from the community science team. And in particular, I wanted to acknowledge researchers, solar system experts that worked on the simulation, on DP0.3 simulation. This notebook was based mainly on a notebook by Pedro Bernardinelli, and then in part in another notebook by Meke Schwamm. And as I mentioned before, we've been trying to keep in mind and follow the accessible authoring checklist that I mentioned before that we're going to go through in depth in a future assembly. Okay, so you have the usual websites where you can get support and documentation for the simulations that we have. And then first, we have a little bit long introduction. Usually I try to be a little bit verbose with when I write tutorials, but at the same time, it was also for me as a learning opportunity to learn the definitions of the definitions that would be relevant for this tutorial. So first of all, as I mentioned before, we have the Trans-Neptunian objects that are any minor planets within the solar system that orbit the sun at an average distance greater than Neptune at more than 30.1 astronomical units. You can more or less group these objects into 2 populations, something that is hot and a cold population. Usually you have the idea that to have some planetesimals that form inside within the inner region of the protoplanetary disk, and then at some point you have Neptune migrating in these theories and then interacted with this population and then pushed them forward beyond the orbit of Neptune, and then gave them somewhat higher inclination among other characteristic orbital parameters. Or you could also have planetesimals that form directly in situ or in place, and these form directly in the Trans-Neptunian region, and this is what we call the cold TNOs. But then at the same time, we have these dynamical classes, and then it's important to have these definitions because one of the goals of this notebook is to reproduce a plot of orbital parameters that we find in one of the papers in the literature, in particular a paper written by Pedro Bernardinelli using the dark energy survey to find 814 TNOs. So we're going to have the different types of dynamical classes within the TNOs. We have objects that are resonant, that are in mean motion resonant with Neptune. These are called the resonant TNOs. So then we're going to have other types of objects that we call scattering TNOs that have that are actually current. We think that they were actually scattered by Neptune at some point, but they are still experiencing variations and perturbations due to the presence of Neptune. We have another population that is very interesting, which is called the detached TNO population. That in contrast, they have like a higher perihelia, which is the closest distance to the sun, and are dynamically independent from Neptune, and that's why they call detached. And this is an interesting population because there's a lot of open questions regarding these populations, and it's one of the most enigmatic ones. And if this is a population that we want to also study in detail. Another population is what we call the extreme TNOs. And then here we're talking about objects that are very, very far away, that have a semi-major axis in their elliptical orbit, the size of the orbit, that is greater than about 150 astronomical units, and perihelion distance, this parameter Q that we're going to talk about throughout the notebook, that is greater than 40 astronomical units. This is another population in which their formation is a little bit unclear. And in particular, their clustering, we know only a handful of these, and please, Sarah, correct me if I'm wrong, and by a handful, I mean of the order of 20 or something like that. But if you do an analysis of the orbital elements of this type of objects, you can see preferential clusterings. This is a hot topic of debate, but then the clustering of the different orbital parameters of the extreme TNOs offer evidence in favor of the existence of another planet in the solar system, which is called as the Planet 9 or Planet X hypothesis. However, this is still being debated, and if we don't have Planet 9, then we don't need these extreme TNOs. Then we have these classes, and then we're going to have these classical TNOs, which are objects that do not correspond to the previous classes, and that are situated between a particular resonance in Neptune, between two particular resonances, the 3-2 and 2-1 mean motion resonances for a given distance, and they tend to have lower eccentricity and inclination. So we're going to have these different classes that we're going to aim to study the different properties as orbital elements, or even in the LSST, we're going to want to look at the colors of these objects, and the different properties are going to tell us about different models of formation of the solar system. I just mentioned colors of TNOs, but if you look carefully in the DP0.3 simulation, I believe we don't have colors for this particular of objects of TNOs. We do have colors for other objects, but not for TNOs. But that's a limitation of the simulation, but that's okay. And then I wanted to mention comets, which are not TNOs, but I made the choice also to plot them or analyze them in one of the plots that I'm going to show in the notebook, because I just thought it was interesting. But yeah, that was a choice, and they're not technically TNOs, but you find two types of comments. You can have like long period comments, short period comets that have periods of less than 200 years of orbit, or you find other objects that even have even greater orbital times, and then may come from what is hypothesized to be the Oort cloud. Okay, so that was a lengthy introduction, but I wanted to just mention the classes, and because we're going to be looking at the different properties of these classes. And then I encourage all of you to look at the main references that we have for that I looked at for this for the creation of the notebook. In particular, I mentioned this paper, Bernardinelli et al. From the Dark Energy Survey year 6. And let me see if I can show the plot that we want to reproduce here. So this is a paper that used the Dark Energy Survey, which by definition, it was actually trying to do it is a survey, a project that is trying to do cosmology, but it also took a lot of data that allowed to discover about 814 Trans-Neptunian objects. And in this tutorial, one of the first things that we want to do is to reproduce this plot from this paper, which is a plot of the eccentricity in the y-axis of TNOs as a function of their distance of their semi-major axis. We also have the inclination in degrees, and yeah, this is one of the things that the objectives that we have with this tutorial. So I just wanted to mention that. Okay, then we have other references, a review about the TNOs by Gladman and Volk. And then we have another survey that is actually dedicated to find Trans-Neptunian objects that is called the Outer Solar System Origin Surveys, or OSOS, and a textbook on orbital celestial mechanics by Morbidelli et al. So those are the references. Then we move to a section in which we define the packages that we import. So we have the standard packages from NumPy, AstroPy. We have a statistical library, plotting library that is called Seaborn. It's actually only used in a small part in this notebook, but I wanted to showcase another tool or another library in order to visualize these objects. Then we have the tool that is going to allow us to retrieve the data, the TAP service, the Table Access Protocol service, in order to access the DP0 catalogs. And this is a tool that we use in all our notebooks. So we start by defining functions and parameters. One parameter that we're going to use a lot, of course, is the distance, the mean distance to Neptune in astronomical units. Another function that we're going to use is the diameter of a TNO as a function of what is called the absolute magnitude H. So this is an important magnitude, an important quantity within the solar system. You can think of it as a proxy for size. You can see that the function also depends on the albedo or the reflectivity of an object. But for a given albedo, then you can have a certain magnitude being as a proxy of the size of the solar system objects. And I encourage you to look at the next tutorial, tutorial number 4. And tutorial number 4 is split in 2 parts. But the first part of that tutorial has a nice explanation of what this absolute magnitude H is. And it's basically a magnitude that takes into account the distance of an object, in the solar system, the distance to the sun and the distance to the Earth. So you can actually define a function like a phase function, like this H as a function of this phase angle that is here. And then when this phase angle is 0, like here, is when you have this H absolute magnitude that I'm talking about. And these phases is like the phases of the moon, but doing something analogous with the objects of the solar system. Okay, I don't want to go too much into that tangent. I'm just going to say that there's a more detailed description of this parameter in the other tutorials that I encourage you to look at. So this is just a helper function that helps us make a relationship between the absolute magnitude and for a given albedo and the physical size of a TNO in kilometers. Then we have other helper functions, and actually I should have been running this. So luckily the first ones don't take that long. So let's see. There you go. Then we have other helper functions that are going to allow us to define the orbit of an ellipse of a TNO as a function of the orbital parameters, of the orbital elements. We have this Q vector, which is basically telling us about the shape of an ellipse. Actually, this Q3 is a two-dimensional shape, so this Q3 component is 0. But you have the definition of the two components of the shape of the ellipse in the frame of the ellipse as a function of what is called the eccentric anomaly, which describes the position of the object along the orbit, the eccentricity, and the semi-major axis. So these three orbital parameters. So we have that helper function defined here, this Q vector. And then we also have a couple of helper functions that are going to allow us to do a coordinate transformation between the plane of the ellipse and then another Cartesian frame of reference in the it's an arbitrarily orthogonal Cartesian reference frame X, Y, Z. So you can go from that ellipticity vector to the other coordinate frame by using a rotation matrix that is going to depend on other remaining orbital elements. In particular, this longitude of the node, omega, that I'm used to omega being dark matter or stuff like that. But here is capital omega is going to be the longitude of the node. And we're going to have the argument of the perihelion, lowercase omega, and the inclination of the orbit. So that's basically what it's doing. It's a rotation matrix. You have all your sines and cosines. And then I also wanted to point out, if you want a more detailed explanation of the derivations of these equations, you can look at these textbooks. The first chapter of this textbook, Morbidelli et al. Okay, so then this is these are the helper functions that are doing those coordinate transformations, and then we're going to have another few other helper functions. Just to make our plots a little bit prettier and a little bit complex. You're going to see what I'm talking about. So I don't want to go a lot of detail into this gradient field function, but it's basically a function that is taken basically from a stack overflow, and it gives us a nice color gradient under a certain curve. So this is gonna, again, it's a helper function to make our plots look a little bit different. We have another helper function to implement the Kepler's third law between the period, the rotation period, and the semi-major axis, the orbital period and the semi-major axis. And this is a helper function to plot where the resonances with Neptune are. So we're just basically implementing this Kepler's law. Then a few more standard functions to histograms. And again, I don't think I need to go a lot into the details of that. We're going to use these functions in order to look at histograms of different orbital parameters, because that's going to be it was going to tell us the different dynamic classes and then how they relate to different models of the formation of the solar system. And then finally, I think, and I hope, we have one more function to just create subplots. We have then another cell that tells us, again, this is just to make our plots prettier. And these are just particular choices that were made in order to make the plots look in a certain way. But you feel free to explore that. One thing that we always want to keep in mind is if the color palettes that we use are friendly for people who are blind or who are visually impaired people. So usually in our tutorials, you see that we use a standard palette called like the Tableau colorblind or something like that. Here I'm not using that right away because I wanted the plots to look in a certain way, but I was trying to make sure to implement the accessibility guidelines that I mentioned. One of them is, for example, not relying only on color in order to convey information. And then you might see that there are still things that we need to improve, and I want you to call me out on that, and hopefully we can improve on that hackathon that we're gonna have in a few weeks. Okay, so we're gonna finally start doing stuff. Just if you have any questions right now, let me know. That was a little bit long introduction, but hopefully now we can start doing the nice plots that I promised. Okay, well, so the first thing we're gonna do is we're gonna query this MPC orb 10-year catalog. So we're gonna initialize the service. We get the tab service. We pointed to the solar system objects tab service, table access protocol. As I mentioned before, we have a 10-year catalog, which is the one that we're using right now, or a 1-year catalog. We can, here this giving us an option, but you can explore actually the contents of this table, and that's a good thing to do, to see actually what we're retrieving. So then we have different quantities, and then I'm gonna be interested in just a few of these quantities, in particular the orbital parameters like the eccentricity, the inclination of the orbit. I think I'm gonna also retrieve this H absolute magnitude that I was telling you about, and then there is a related slope of the phase curve that it's also explained in this other in notebook number 4. You can see that it's a function that depends on a slope parameter and some basis functions. But I'm retrieving those parameters as well. And I think the number of observations and then other orbital parameters that are described here. So this is how you know what the table has. And then we're gonna execute our query in order to retrieve a sample of Trans-Neptunian objects. So this table, actually, if you just execute it without any constraints, it might take forever because it has about 15 million rows. But if you do certain constraints within the query, in particular the constraints about the objects that they need in the semi-major axis quantity A, then it's going to be faster and it's going to give you the amount of TNOs. But let me go a little bit more in detail in what is being described here. I think this is just explaining a little bit more what I just said, the type of parameters that I'm retrieving, the absolute magnitude H and the slope parameter G related to that. This is what I just mentioned, the constraint on the semi-major axis. The table doesn't have an explicit column that gives you A, so you need to use the relationship between the perihelium parameter and the eccentricity that gives you A. So you can do a where constraint here with the columns of the table, and then you can have that built in the query. Then I also selected a minimum number of observations in order to have more statistics. And then I did a joint search between the ID of the MPC orbital parameter, MPC orbital catalog and the SS object catalog. So then we do the joint query by object ID. So this query should give us about 27,000 TNOs. There's a typo here that I need to fix, but that's fine. And it didn't take much, so that's great. And currently we are known about, we have the number of TNOs that we know, it's about 1 order of magnitude less, of the order of 4,000 or something like that. This is consistent with what is expected with LSST year 3. Although in some sources in the literature, I think it's quoted a little bit more, like about 40,000 TNOs. And I believe that is part of some of the limitations of the hybrid simulation that is being used for DP0.3. But this looks reasonable, like about 28,000 TNOs. I'm gonna calculate then the semi-major axis, and I'm gonna add it to the table that I got when I run the query, this TNOs table that has everything that I need. Just for convenience, I'm just gonna define this as A, as an extra column. And then now I'm going to start exploring these dynamical classes of the TNO. The first thing that we can do is just to plot the eccentricity and inclination as a function of semi-major axis. Here we have a limit in astronomical units here in the x-axis, but let's see what happens if we just take off that limit. Then we have a plot like this that has a lot of white space, because we do have objects that are actually that have very long semi-major axes that are like, we can explore a little bit more about what those objects are, but this is not very informative, right? So that's why we have this constraint in the semi-major axis. So then here we have a plot that it's a little bit more informative, and then can start showing us some structure in the distribution of the orbital parameters of the TNOs. If you look closely, then you can start see some clustering here in eccentricity. And then if you look at the paper by Pedro, then you know that these are the resonances. But then, as I mentioned, we want to make a version of this plot that resembles a little bit more what it's in this paper by Pedro Bernardinelli. So this is a good start. At this point, I also wanted to showcase a different way of maybe plotting these quantities. So it's basically what we're going to do in the rest of this first section is just to plot the same thing, but in different ways. It gives us maybe more insight in what we're looking at. So here in this cell was taken from a notebook by Meg Trump that uses this Seaborn statistical visualization library. And then you can have like a different type of displaying of representation of these same parameters here. But it's basically the same stuff. But I just wanted to put it there as an example. So this cell explains the clustering in the semi-major axis that I was talking about in terms of the resonances, the mean optical resonances of Neptune. So at the beginning, so then we move forward to the next subsection. At the beginning, I was talking about all these different dynamical classes of TNOs, and then how do we actually define them, or how do we actually make cuts in order to get subsets of the table that I have to identify each one of those classes? So, well, you can look in the literature, or you can ask your solar system experts friends, and they're going to tell you, well, the classicals actually have a certain range of ellipticity, the scattering have, and this is mentioned at the beginning in the introduction, they have a certain Q greater than such and such. So here we're defining these bounds that are going to allow us to make these subsets from the TNO, the main TNO sample that we retrieve. So there is a caveat here, no? There is a warning. These bounds here are approximate, they're kind of fluid, so to speak. If you read the papers in the literature, the way in which these dynamic classifications are done has to do with integration of orbits, and then you do cloning of orbits, and there are more robust criteria in order to actually do this dynamical classification. So you can look at section 5 of the paper by Bernardinelli and all that based their criteria on other papers by Gladman and Volk. So just to have more details, and there's that warning, right? But for the purposes of this notebook, we're gonna work with these bounds, with these boundaries. So here I'm just making all the cuts for the classical, for the detached, for the scattering. Then you do all the logic, and then you create your mask, and then you get these are the masks. And then here later I define the actual data. But before, so these are the masks for each individual class. Here I decided to add another column in the table that has the name, just a string that has the name of the class to which each particular object belongs to. So I initialize it with a string, with a blank string called other, because even after doing all these cuts, there's gonna be objects that don't fall within that that category. Let me see, is there a question in the chat? Let me see. So Bob is asking, do the classifications overlap so that one asteroid might be found in more than one classification? Yes, I think that's what I meant by fluid. So here we're talking about TNOs, I guess, not asteroids, but yes, I think that's what you find. At least this I don't know how to call them. This maybe informal cuts or fluid cuts. Then when you do the more strict cuts, then I guess there are I don't know if a particular object can be classified as well as in one class or the other at the same time. From what I was reading from Pedro's paper, you have a solution and integration, and then you do like 30 clonings of the orbit, and then you apply certain criteria. And sometimes like 80% of the orbits end up in one class, but then like 20% ended up in a different class. So that's what I know about this. And please, Sarah or someone else interrupt me if there is something more to say about this. Okay, so yeah, thank you for your question. So as I was saying, then this is here just adding an extra column with the string. So as I said, even after doing these cuts, then there are objects that don't fall within this classification. And then you can notice that we don't have the resonant classes here. That's one of the exercise left for the reader. So among those others, you can find also the resonant objects. Okay, so then here we're actually defining the classes in the table, and defining this extra column class. And then we're defining the unique value of each class here. Here we're confirming the number of objects that we have within the different class. So you find about 8,500 classical objects. You find comets, then again, they're not TNOs, but I still included them here. About 3,000 comets. You have then about 547 detached, which I think current data sets have about 150, like the observed detached objects that we have is about 100 or so. Extreme objects is just a few, but still significant improvement on what we have right now. And then about 13,000 scattering objects. Here I'm defining, so we're gonna now get ready to repeat this plot and then try to make something that looks a little bit similar to what it's in the paper by Bernardinelli et al. Then again, this is another convenience dictionary in which we have a particular color, I guess a color palette based on XKCD, I guess. I was going here, so as I said, this is based on a notebook by Pedro, and the color palette is actually based on some of the plots that he produced for his PhD thesis. So I was just following that I wanted to match that art. So that's why we have these choices. But then we have a different symbol for each color, and then we have a different symbol for the lines of each object. Then here we're gonna have a block of code that might be a little bit scary. We're just doing the plot, but it's just you can look at it in detail. But here we're just defining what the resonances are going to look at. We're gonna use that gradient fill helper function that I was telling you about before from Stack Overflow, in order just to have a nice gradient under the curves. And then for every different for the different classes of objects, we're gonna do the same thing. And then here is just different labelings of the plots that you're gonna see. So probably maybe we could refactor this a little bit better, but just don't get scared by that. It's just a plotting cell, and then we have the first plot. Okay. So okay, we have again the same plot, but now with the different classes. Here we have the eccentricity and inclination as a function of semi-major axis. It's a little bit more crowded because we have 29,000 objects instead of 800 objects that has the paper by Bernardinelli et al. But then maybe you can think about different ways of visualizing this. Maybe just doing a scatter plot is not the best, but maybe we can do something different. So yeah, we could do that. But you can see here the different types of the different dynamical classes for the TNOs. I also, as I said, decided to include these long period comments that are at this clustered in this region. And then you can see the vertical lines that are showing us the mean resonances with Neptune. So you can see by eye, and as I mentioned, the resonances are not, they do not have a color and a different symbol here, but that's something that could be done, and it's one of the exercises. You have the detached object, you see the scattering, the steady IU is Neptune, and then you see the scattering, some of them, they're still cross beyond the orbit of Neptune. You have the clustering of the classical objects at lower eccentricity. Sometimes people, here I think we're making a cut in inclination for the classical objects, but then sometimes people also let them have a little bit higher inclinations. But here they have relatively low eccentricities and relatively low inclinations. Well, relatively here is like 40 yeah, sorry, yeah. Here, well, you can see that it's more clustered here at this lower part of the inclination space. Okay, so but then I also wanted to make a better looking plot like that included the extreme objects as well. So we're basically repeating a lot of the code that we have here. And then again, maybe we could refactor this a little bit better, but it's just basically the same thing, including the extreme class. So we have now a nicer looking plot. Actually, maybe we helped make it less crowded. Here, this is just the eccentricity. I didn't plot the inclination, but then we also have more comments and then the extreme class. So this is a plot that then shows what to expect with LSST, and is one of the plots that we're hoping to make with the actual data. Okay, do we have any questions up to this point? Because then we're going to move to another section to make histograms. Okay, all right, very good. Keep the questions coming. I see Sarah is answering questions in a more robust way, so great. Thank you very much. All right, so what else can we do? We can make histograms of the orbital elements. So here, in order to better characterize these dynamical classes, we can retrieve different orbital elements, such as the longitude of the ascending node, the argument of the perihelion. We can look at the estimated diameters. We can assume an albedo. So we actually, as I mentioned, if you want to have a size, that's a function of this absolute magnitude h, but also it depends on the albedo. But if you fix the albedo, which, take that with a grain of salt, and that's another exercise for the reader, like what happens if you actually change that albedo assumption for something more, maybe that allows for a distribution that you can find in the literature. These are some of the references that we use in order to find a number for the albedo. But for now, we're assuming a fixed number for the albedo and just plotting the size once you get the absolute magnitude h. One of the things that we want to see if there is any clustering of the orbital elements, and then let's see what we get. We actually okay, so that's the explanations. Here what we're doing is just excluding the comments. So we're done with the comments. I just wanted to show them here because I think it's cool. But then now we are excluding them from the TNOs. We're going to calculate, we're going to use the helper function in order to calculate the diameter of the TNOs using the MPC-H, the absolute magnitude. We don't pass an argument for the albedo because we're using the default of 0.1. And then we add another column to our table of TNOs. And then we have one cell block that is going to show the histograms of the parameters that I was talking about. So we have the label is here in histogram number 4. And I don't know if maybe I should make this a little bit smaller here, just for a second. Oh, well, let's leave it like that. Big. So let's look at the histogram. Number one, we have the in logarithmic space. Then we have the longitude of the ascending node. The second histogram is telling us about the argument of the perihelion. And then looking at those two histograms, then we have this dotted line is that the other class that I was telling you about. But then the other classes that we have, the actual classes is the classical, which is this purple dotted here. Then we have the detached, which is this dashed one here. And then we have the extreme one, which is the dashed dotted line right here. You can see, for example, the classical one has a little bit more uniform distribution of these two parameters. You can see some clustering of, one of the interesting things is you can see some different clustering, or you don't have a uniform distribution for the extreme class. Then again, take it that with a grain of salt, but it's just an example of the kind of things that we would like to find. But why do we take that with a grain of salt right now? Because, okay, we don't have a lot of numbers. And also, it might be, there's a warning here, there's a caveat. It might be a limitation of the model that is used. And if you look at the previous delegate assembly, then which we had Pedro Bernardinelli and Jake, they were some of the people that helped create this simulation, DP0.3 simulation, which is a hybrid simulation based on a model called the Pan-STARRS synthetic solar system model. This is a model from published in 2011. Many of these extreme TNOs were actually discovered afterwards in surveys such as OSOS and DES. So there might be discrepancies as well, but this is just to point out the caveats. But yeah, you see that you don't have a uniform distribution in the extreme classes. Then we have and the histogram of the estimated diameter that is cut at 400 kilometers, so you can play and see if there are objects that are higher. And then again, another exercise is to what happens if you put like more realistic albedos for each class. If you look at the papers, at the papers in the literature, again, the paper Bernardinelli et al. From the DES-TNOs, you find this kind of histograms of cumulative functions, right? And then you can see different cumulative functions from the different classes. And there are different models of formations of the solar system that are going to assume certain, are going to have different assumptions, and then are going to produce different predictions for this type of cumulative histogram. So that's also another observable or something that you can tell in order to differentiate these models. And there is in section 5 of Bernardinelli et al., there is a discussion of does what we observe match this model, one of the particular models of the formation of the solar system that is produced. I don't know if I mentioned the model here, but it's yeah, this CFEPS L7 model or something like that. But the information is here in the introduction to this section. Okay, so another thing that we can look at is the G parameter, again, the slope of this H function, that it's the slope of this reduced magnitude as a function of phase angle. But for TNOs, we actually find the same. It was in this particular simulation, it was assumed that it had the same slope. So we're not going to make a histogram of that, but we just wanted to verify and look at that the minimum and maximum values for each of the classes is the same. Then as a summary is what I have been repeating, that the distribution of these TNOs orbital parameters and the properties such as and also the absolute magnitude H and the size, they gives us insight into the physical characteristics and the evolution of the various TNO dynamical classes. And then another thing that I mentioned before is the different colors. That's another interesting thing in order to look at the different colors of TNOs for different dynamical classes. And then see, you can also place constraints on models of formations of the solar system based on that. That's one thing that I wanted to do, but but for the simulation, that's a limitation that cannot be done. But that's another thing that is done, looking at colors of TNOs. Okay, just to finalize, we have two more sections. We're going to do a visualization of the orbits of the dynamical class, and then we're going to use some of the helper functions that we had at the beginning, again, which is taking the orbital elements. We can define an ellipse for the orbits of the element of the TNOs. Then something similar, if you look at other notebooks like notebook number 2, there is something similar done there, and it's just done in a slightly different way, I believe. But then it's good that we have another way of showing this. So what's happening here? So we're gonna calculate the ellipse. We're gonna use the function full ellipse, the helper function, for all the TNOs that receives the orbital parameters, and then it gives us the parameters of the ellipse. So we're gonna do a loop over the TNOs that we have, and we're gonna calculate an array that is gonna have the ellipse for each object. Then we're gonna plot just the first 100 objects because I didn't want to make it too crowded, the plot, but then again, you are more than welcome to explore different ways of visualizing this data. So this is an example of what you get, which here we don't have it disaggregated by classes, but this is something that we can do here in the next step. So here this is a plot of the ellipses in the plane of the solar system in terms of the axes are the distances in AU, or sizes of the ellipses in astronomical units. Then so we can define a function. We can define a for loop for each class, and then see what these orbits look like for different classes. And then we have this nice grid here, and you can see the classical orbits are more or less circular because the way in which they're defined by definition. Of course, you have the scattering with the different ellipticities as well, given by the constraints, and not the same with the detached. You have the extreme objects that, as I said, they have a very large semi-major axis and a Q greater than 40, I believe. Here, one interesting thing, and then again with the caveats that I have mentioned before, is that I think you don't see a lot of clustering in a space of the perihelion of these orbits. If you look at talks by people that propose the Planet 9 hypothesis, like Konstantin Batygin and Brown, you see that they made this type of plots for the existing data that we have, and then one of the observations to support the existence of Planet 9 is there seems to be a clustering of the orbits, of the perihelion of the orbits in a space. So that's very oversimplified, but that's one of the lines of evidence in favor of the potential existence of an extraplanet in our solar system. It's a hypothesis that is also, it's a hypothesis, so still under debate. But that's an interesting thing, because when I was discussing this with Pedro, we were saying that this is cool because then LSST is most likely probably is going to give us the data, enough data to have an answer to see whether there is a Planet 9 or not. So the last section, so that's just a section to visualize the orbits. And then this last section, we wanted to focus on one TNO in one of the deep drilling fields that have a lot of observations. This is the one example that you also find in one of the tutorials of the portal aspect of the RSP. Because we also wanted to illustrate how something that you can do in the portal, how you would do it in the notebook aspect of the RSP. In addition of illustrating the movement in time the change in position of the TNO as a function of time on the sky. So then again, we used here we're gonna use the DIA source catalog. We're gonna use a deep drilling field in order to have a lot of observations. And then over the 10 years of the survey, these drilling fields are gonna have produce a lot of observations on TNOs. We do again a query of an SQL query here of the position of the right ascension, the declination, and then the median, the day, right? The midpoint of the effective mid exposure time for the source. And then we retrieve the particular source ID from the tutorial, one of the tutorials of the portal. So we just select the object, and then we do a plotting of the orbit, and then you can see the movement of the Earth, and you can see the epicycles, and then you can see how as a function of time. So we have in the y-axis we have declination, in the x-axis we have right ascension, and the color bar is telling us about the time, right? So it's you can look at the bar, then you can see how it actually moves in time. This is a plot that afterwards, like if I printed this in black and white or something, would you be able to convey the information that the bar is given? So maybe not. So maybe something better could be done there in terms of accessibility. But that's a thought, and it's just to encourage everyone to also always try to examine as you do your research, how can I make this more accessible? Okay, so that was our final example. Then, as I mentioned, there are some exercises for the learner, for the reader. I mentioned one possible exercise is just try to define a resonant class, and then try to include them with a different symbol in the eccentricity, inclination, and semi-major axis plot. You can also try to get a better estimation of albedos for different dynamical classes, and then calculate the sizes using the absolute magnitude that we have. And then I also mentioned the cumulative distributions of age. This is what we calculated, but you could also calculate other cumulative distributions for other orbital parameters, and this is also a nod to this particular section of this paper, that has been central to this tutorial, Bernardinelli et al. And see what you get. Okay, and that's it. 1 hour. Do we have any more questions in addition to that has been asked already in the chat? Thank you, everyone. Feel free to ask questions, or then I guess we can move on to the breakout sessions if there is interest. Let's see. So how do we manage this part, Melissa? Because I don't know how to put people in breakout sessions, or maybe I can give a little bit more of time to see if people want to ask or want to discuss, or maybe time to Sarah to correct anything that I have said. I'll be grateful.
Yeah, we can take questions while you bring up this slide that has the list where we can make the breakout session topics.
That's good. Hold on. Let me stop sharing for a second.
I think we just have a few delegates left here, and typically this is the part of the assembly where we let the delegates say what they want to do with the last hour. In particular, if you want to make a breakout room and go and work on those exercises for the learner, we can do that, and Andres can go in and help you try to work through those. If you've been working on something else related to DP0 and you'd like to talk to Ruben's staff about it for a bit, we'll make you a breakout room. We'll figure out who could best help you. You can have a chat. does not have to be a full hour. You can chat for 10 minutes and that's fine. We'll just help you with whatever problem you have. But this is the time for delegates to say what you might want to do. And occasionally nobody has questions, and that's also fine. So just give it a minute, and if you'd like to suggest a breakout topic or something you want to work on in the chat or by unmuting. I think we are down to one non-staff person now.
So I'm just running all the regression, sklearn regression techniques. So I'm running like 26 different regression techniques for colors and magnitudes, and then trying to optimize them. So I don't really need a breakout room, but I just thought I'd let you know what I'm doing.
Okay. You're doing like stellar color stuff.
So I have I created a set of white dwarf, M dwarf binary systems, and I have absolute magnitudes from 8.5 to 14.5, and Sloan colors for all of them. And so I'm just trying to see what I can fit, and I'm just using it as a way to learn all the regression routines in sklearn. So I've got them all running, using some help from AI, and I'm just trying to optimize them now so I can learn how they work.
Okay, excellent. Yeah, using DP0 to learn new software.
Mm-hmm.
Awesome.
So I don't need a breakout room.
Okay.
I don't think I need one either. Okay. I just wanted to say to Andres, I like the way that you put the paper references incrementally throughout the notebook. That way you can zoom in on something that you may not be familiar with, and get into the details, as opposed to having to, get into it like in the papers themselves at the very end, where you have to wade through it all and try and figure out what the topic was that you actually had the question about to begin with. Yeah, I like the way you did this. It's very nicely done. Thank you.
Thank you so much, Aaron. Yeah, thank you. I think that's a great feedback. Thank you. And I think maybe, hopefully we can do it also. I think we're doing it also with other notebooks, and then we can see how a notebook can provide added value as opposed to reading a paper. Well, as a complement to reading a paper like this, like as you mentioned. And as I mentioned, it was also a learning exercise for me, which is great. So I was also trying to put the references, and I got a lot of feedback from the community science team. Put a reference to this, to that. So I should also, of course, credit the peer review that we have in the team.
Now, there was one diagram you had with the classicals, in purple. It was that one there. Do you think it's possible to change that purple into a more transparent color? Because I suspect it's overlaying other and the scattering. I mean, it kind of implies that it stands alone when it's opaque like that. But if it was transparent, you'd definitely get the impression that there's a data underneath there for both of those two other classes.
Yes, I think that's a great point. I was struggling a lot with this in the sense that for things like that, for conveying information like that, I had the paper, the original plot by Pedro that had different colors, but you can definitely, this is like the alpha parameter that you have in one of these,
right?
In one of use alpha, right? So you can play a little bit around.
Exactly right.
So
exactly.
You can do that.
Mm-hmm. So if we alter the alpha to 0.6 or 0.5 or something, then it'd be apparent that data is behind it. That's good.
Yes, so so you have to do like a particular alpha for each class, which is doable, right? I'm not gonna try to do coding in real life, but in like life right now, but yes, that's definitely something. And
then the other one was where you had the top down view of each of these type, exactly, those there. That would be very exciting if there was a way in a It's not a criticism. It just, I wondered about it in the back of my head. If you could, if you had it, I think there's ways to do it in bokeh or something like that, where you actually put the cursor above it and rotate rotate your mouse and actually have it rotate out of the plane, so you can see sort of the eccentricity of the orbits. Uh, it that might be something to pursue. Maybe that's something to throw at the end. Throw that on the student, as an exercise. But
yes, absolutely. Yeah, thank you
because
very much for the suggestion. Yes.
yeah, to see how you got some extremely elliptical in the lower right, and you've got some extremely circular, and it'd be interesting just to see if they all lie in a flat plane, as opposed to the extreme, if they splay, which I'm just guessing that they do. Yeah.
So you want to rotate them to see the inclination as well?
Yeah. Yeah.
Okay.
Yeah.
Yeah, I don't know. You can do that. Probably you can do that. And we do have some tutorials with interactive plotting, like using bokeh, one of the first DP0.2 tutorials. So yes, that's definitely something that can be explored as well. Yeah, thank you for the suggestion.
Yeah. It's a beautiful notebook. It's absolutely beautiful notebook, and wonderful. I can't wait to dig into it with some AI. So
Thank you.
yeah.
Yeah, I suspect 3D plots, probably something that's going to come out of Sarah's first ticket, because basically, Sarah, you have that ticket to look at these other plotting packages, and I think there's 3D stuff in there. And so a notebook full of just like cool plots, so you can copy paste and use cool plotting techniques like that. I suspect that'll probably, because I don't think we have a 3D plot in any of the tutorials yet, but of course solar system stuff is perfect for that. So I suspect we'll be adding some soon.
Yeah, there's so many great things in this notebook, especially like the resonances that were shown earlier. And you get the lines shown for certain resonances, but then you see in between those, you can see little patterns again. Yeah, even there, you see sort of a clustering in the scattering data there. So if you have uh, a penchant for exploratory data analysis, it's just like an invitation to go in there and see what else you can pull out of it. Yeah. Thanks for sharing it.
Yes, absolutely. And as I mentioned, yeah, it was based on Pedro's notebook and Pedro's code. So yeah, that's also great that they have been sharing all of the cool tools that they have. Let me see if I had Pedro's original plot. I think it's something like this, what Pedro had. This is a presentation by Gary Bernstein, which was my supervisor in cosmology and also Pedro's supervisor in solar system stuff. And I think this is Pedro's version of the plot. Which I guess, yeah, maybe we could change. Still, I just wanted to see if you could differentiate what you were pointing out in terms of the scattering.
Oh, yeah. Bernstein gave a really great talk on this at the DES collaboration meeting yesterday or the day before.
Yeah, I missed that, but I don't. Unfortunately, I looked at this on YouTube. This was a seminar in Chicago last year or 2 years ago, but maybe I don't know. Yeah, maybe one of those seminars we can invite.
Yeah, some really nifty graphic animations too. Maybe I can find one.
Yeah, they have a student who made a very good. This is a static.
Oh yeah. She did it. Yeah, about the how things are going to evolve. The orbits are going to evolve over the next few thousand years.
Yeah, wonderful.
One thing
And
that
I asked if any of them had achieved escape velocity, and it could be our own interstellar uh comet for other would we export any interstellar objects just yet from our solar system.
yeah.
Yeah, you know, when I see those large the graphs there, like the one on the screen, um, I have an urge to you know, the new, I know you're going to say, quit saying the word AI, Al, but the new multimodal AIs, you can put in graphs and figures now, and have the large language models give you their interpretation of what's going on there. So it'd be interesting to take some of the graphs out of the papers, um, you know, chop off the figure description, give it to the AI, and ask it for its considerations, you know, on what's in the data there. And it'd be interesting to see if it actually pulls anything of any intelligence out of it, you know, rather than hallucinating an answer. I know it's, I tell you what I'll do is I'll do an experiment like that, and I'll get back to you guys and let you know if anything of substance comes out of it.
That'd be
Because
great. And I was going to encourage you to pursue that, of course. And then if you have something you want to present, that would be great.
yeah, it's hard to say if it could extract anything out of it, but I mean, it would. I'm sure it would pick up on some of the terms inside, like, you know, comets, and it's just hard to say what it would get out of it at all. Then if you give it a little bit more data each time you input it, you know, like if you gave it the figure caption, um, it might give you something more significant. But yeah, I think I'll take a note and do that as an experiment in the next week or two.